Okay, so what I want to talk about today, which will not be on the test, I want to say a few more words about uniform continuity, and then go on to the next section, which is about the intermediate value theorem, one of the classic value theorems from calculus. Today, though, more about uniform continuity. One last thing to say about this. We've done many examples about uniform continuity before, and I hope that you are beginning to get a feel for what it's all about. For example, if I look at, say, x squared, this parabola, f of x equal x squared. This is not uniformly continuous on all of R because the function continues to go up sort of forever as I go out to the right or to the left. This is not uniformly continuous on all of R. But it is if you just look at a particular bounded interval. Then the values only go up so high, and then it is uniformly continuous on that bounded interval. So it's not uniformly continuous on all of R, but it is uniformly continuous on, actually, for this particular example, it's uniformly continuous on any bounded interval. If you recall this, when you're doing the proof that things are uniformly continuous, usually you kind of separate out one part, which is fine, and then you have a bunch of leftover stuff that you have to use inequalities to say why it's bounded. This other stuff is always less than 14 or something. That's how we did some proofs last time. That extra step, this part is always bounded, is generally, that's going to be, that's only really possible to do when you're looking just at a bounded interval. If you have some upper limit to what the x can be, that's what allows you to say this whole part is less than or equal to some specific number. All right. So that's true of this example anyway. This is not uniformly continuous on everything because for the unbounded part, it's not uniformly continuous there. But it is uniformly continuous if we concentrate only on some bounded interval. Here's another example. How about 1 over x? This is f of x equal 1 over x. I wrote 1/2. 1 over x. This one also is not uniformly continuous on all of R, but here it's not because of the far out parts, it's because of the parts near 0, which make it not uniformly continuous. So this also is not uniformly continuous on all of R, but it is uniformly continuous on, can I say where is it uniformly continuous? Actually, I shouldn't have said R. Can I just say, really what I meant is R minus the origin, R minus 0, because it's not even defined, like 0 is not part of the domain, so we typically wouldn't even talk about if it's continuous including 0, but it's not uniformly continuous on the whole domain. What about individual intervals? Like, is it true in this example also that it is uniformly continuous on any bounded interval? So like if I only take a little chunk like right here, then actually it will be uniformly continuous just on this little piece here because the function is bounded in there and there's no problem with making upper bounds for pieces of the function. Although, something interesting, it's not actually uniformly continuous on a bounded interval. Can anybody tell me an interval where it's not uniformly continuous? Really, the issue in this function is not going out to infinity this way. It's really about this part here. You got an idea? He said -1 to 1. That's a good answer, although I would say you can't really use an interval which includes 0 because that's not part of the domain. Can we do it in an interval that doesn't include 0? Yeah?
Could you do like 0 with like an open bracket and 1?
Yeah, so this is not uniformly continuous on, even on, say, the open interval 0 to 1, right? Because the function, I mean, this is not exactly why, but the proof won't work out because the function is unbounded on this interval when it approaches the 0, even if I don't include the 0 in the interval. if we allow the domain, all these other domain points approaching 0, then you're still going to get the same kind of behavior. It's not uniformly continuous on 0, 1. It is, though, it is uniformly continuous on intervals. Can I just say intervals away from 0? Right? If I took some other interval over here, then it will be uniformly continuous on that. Right? Intervals away from 0 would be fine. Yeah?
Would it be, does it also matter, like, if the interval is not, like, something way out to the right, or could it be, like, on the right side?
In this example, it could even go all the way to the right, because this function is not much is happening with the function in this particular case, although in this example, it's not allowed to go all the way to the right. All right. I want to talk about some kind of general principles here about what kinds of sets for the domain, what kinds of set will make it uniformly continuous. I want sort of a theorem that says something like, this is what I'm looking for. Something like if f of x is continuous, that is point-wise continuous, not uniform, but just like ordinary continuity, and let's say K is some set has some kind of property here, then F is uniformly continuous on K, right? This is the kind of theorem that I want to be able to say. What types of set will make it uniformly continuous? If you already know it's continuous point by point, what kinds of sets can you choose to make it uniformly continuous? So we've seen already actually an open interval may not do it, because this is an example of a function which is continuous at all points of its domain, but I used an open interval and it wasn't uniform continuous. This one, not uniformly continuous on all of our, actually if you allow the interval to go out forever on one side, then the function may no longer be uniformly continuous. So what goes in the blank here? I would say open intervals are not allowed, because there was a counterexample where sometimes if you have an open interval, it will not be uniformly continuous. Also, unbounded intervals are not allowed, because sometimes if the interval is unbounded, it won't work. Right? What about a closed interval? Can you always use the closed interval? I said here, this one will be uniformly continuous on any intervals away from 0. Now if you think about it, I think actually any closed interval here will automatically be away from 0. Like a closed interval, it's not going to include 0 because 0 is not part of the domain at all. But any other closed interval, even if it was kind of close to 0, is still going to avoid 0, right? And the fact that it's closed means it does not approach 0 like kind of infinitely closely. Actually, I think a closed interval would work here, although it can't be It seems to me a closed interval will work here, although it can't be unbounded. It has to be closed and bounded. Does that remind you of anything? Yes, if you remember the Hyena-Burrell theorem. Actually, what goes in the blank here is any compact set. And this is sort of our big theorem about uniform continuity. If I have a continuous function and the domain is a compact set, then the function is automatically uniformly continuous on that domain. So I'm going to write that as a theorem. I do want to talk about the proof of this, and then we'll go on to the next, the other thing I wanted to say today. So this is a theorem. This doesn't really have a name, I don't think, but it's an important theorem about uniform continuity. It says if f is continuous pointwise, I'll put that in parentheses, pointwise. Pointwise just means like ordinary continuity as opposed to uniform. So if f is continuous and K is a compact subset of the domain, then f is uniformly continuous on K. It's all about compactness. All right. This proof will get into some details about compact sets, but I thought that this would be appropriate anyway. I mean, this theorem per se will not be on the test, although what will be on the test are things about closed and bounded and all of that stuff. So pretty much everything that I say here, I hope, will be a nice little review about compact sets. I don't know if you've thought about compact sets in a while, but this is very much about compact sets. So if f is continuous and K is a compact subset, then f is automatically uniformly continuous on K. You should imagine K is something like a closed interval, a bounded closed interval, but it doesn't have to be an interval. It could be some stranger kind of compact set. It could be like a union of a bunch of intervals, or even something like the Cantor set, which is a compact set. All right, let's see if we can do this. It's not, you don't need a lot of big ideas for the proof. It actually sort of comes out nicely if you just play around with the definitions. So we are going to assume that f is continuous. Let f be continuous. But I'm going to do this whole thing by contradiction. And I'm going to say for a contradiction, assume that it is not uniformly continuous. On K, right? Then, anybody recall, what does it mean that a function is not uniformly continuous? This we usually prove it in terms of sequences. Anybody remember what does this mean about? Then there's some, I'm going to say there's some sequence such that blah 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 blah, something like that. Yeah.
There exist two sequences, x and y,
Yeah.
such that x at absolute value of x and minus y approaches 0, and the absolute value of f of x and y does not approach 0.
Yeah, great. She said it right. I wrote it wrong. Excellent. So I hope you all remember that. This came up on the homework, I think. I don't know. Did you do the homework? This is what it means when a function is not uniformly continuous on a set K. You have two sequences in K, so that xn minus yn goes to 0, and f of xn minus f of yn does not go to 0. All right. Here I'm about to say the only kind of idea which is slightly out of the box in this proof. The rest of it is all just about sort of, do you remember definitions of things? But one thing that I'm going to say is actually we can assume that f of xn minus f of yn is bounded away from 0. I'll say what I mean by that. Not only does the limit not equal 0, but these things here, that difference never actually equals 0 or approaches 0. Remember, when I say this does not converge to 0, it could mean it converges to something else, or it could mean there's some kind of oscillation. Like maybe this thing doesn't go to 0, but maybe it's like if its values are like 0, 1, 0, 1, 0, 1. That doesn't converge to 0, but it still equals 0 every other term, right? But I'm saying actually, not only this does not converge to 0, but we can assume that this sequence is bounded away from 0. That means these terms never equal 0, and they never get extremely close to 0. How can we assume that? It's because if this sequence does not approach 0, it means, now, like I said before, it could be it doesn't approach 0, but it still has zeros in there like infinitely often. It's just sometimes goes to other values too. But since I'm choosing any sequences at all, I can just choose a subsequence of these. If I have this already not converging to 0, I can just throw away any of the terms which actually equal 0. And so that I get a sequence where not only does it not converge to 0, but it also never equals 0. And in fact, you can throw away all the terms that are even close to 0 and get a subsequence which is, like I say here, bounded away from 0. All right? That means that these terms do not, none of them approach 0. Not just that altogether it doesn't converge to 0, but none of these terms approach 0. All right? Even in a subsequence. That's what I'm saying here. All right? Apart from that, the rest of the proof is fairly routine. Now, I have to, at some point, we have to use the fact that K is compact, right? That is the basic assumption. That's what makes the whole proof work. Anybody see anywhere in here where we can use the fact that K is compact? The definition of compact, remember, means if I have a sequence inside the set, then it has a convergent subsequence which converges to a value inside the set. Anybody see anywhere where we could use that fact, that K is compact? Since K is compact, compactness is all about sequences, right? Is there, actually, I think I do see, these are sequences in K, right? And so, because K is compact, it means any sequence in K has a convergent subsequence, and what it converges to is in K. So that's what I'm going to say here. Since K is compact, Xn has a, I'll say it again about Xn, and it's also true of Yn. Xn has a convergent subsequence. I'll call it Xnk. And Xnk converges, I'll say, to X. And X is in K, right? It has a convergent subsequence, and the thing that it converges to is in K. That's because Xn is a sequence in K. Same is true for Yn, so I'm going to write the same thing. Also, there exists a subsequence Ynk. Ynk converges to Y, an element of K. All right? Okay. So these guys, not exactly, but these guys, like a subsequence of them approaches to X, and another subsequence of them approaches to Y, right? That's what we're saying down here. What does this mean? The fact that these terms, their difference goes to 0. Since sine Xn minus Yn goes to 0. Well, that means, of course, this also is true of the subsequence. This is true of the big sequence, but it's also true of the subsequences. This means Xnk minus Ynk approaches 0. All right. But actually, we just said, but also, I can say this approaches, because of this business, Xnk goes to X, Ynk goes to Y. So this also approaches X minus Y, right? The Xnk goes to X, the Ynk goes to Y, and so those guys also approach X minus Y. And so what does that mean? Well, this sequence approaches 0, but it also approaches that. That means these are equal, right? If a sequence has a limit, then it only has one limit. Like this is the same sequence. It can't approach two different things. That means these two allegedly different things are actually the same thing. So 0 equals absolute value X minus Y. i.e., can anyone say that in a simpler way? Any absolute value masters? Nope. You don't have to be an absolute value master. X equals Y. Yeah, they are the same number. If the absolute value of the difference, this you think of this as the distance from X to Y, and it's 0. That means X equals Y. All right. Are we done? That sounds like a conclusion. That's not the end of the proof, but a lot of this stuff then we have seen. So I'm going to try and summarize what we got so far. All right. So, can we summarize? We had this f of xn minus f of yn is bounded away from 0. And we also have the fact that xnk approaches x and ynk also approaches x. Before we said approaches y, but since then we've demonstrated that x equals y, right? So actually they both approach x. One thing which we haven't used yet, we used the compactness to get the subsequences. The other ingredient was that f is continuous pointwise, all right? What it means to be continuous pointwise in terms of a sequence is if this sequence goes to x, then I can plug these into f. Since f is continuous, f of this goes to f of x, right? And f of this goes to f of x. So I will say since f is continuous, pointwise, f of x and k goes to f of x, right? This is the sequential version of continuity. If you have a sequence that converges and a continuous function, it means that you can plug that sequence into the function and it converges to the function's value. I hope you remember that. And similarly for this one. And f of y and k approaches f of x again. All right. And now we're pretty much done here. Anybody see where this is going? We have this is bounded away from 0. That means when you look at the limit, what this approaches, it's not 0 and it's not even close to 0. But remember, and we're looking for a contradiction here. And then also, if you look here, these two things each approach f of x. Anybody see a problem with this contradiction? Yeah? Yeah, right. These two things here are both approaching f of x, then when I subtract them, this should be 0, right? But I'm saying up here that it's bounded away from 0. So that's what I'm going to say. So absolute value f of x and k minus f of y and k actually approaches, when I take the limit, I get f of x both times, which is 0. And that contradicts the fact that this sequence is bounded away from 0. This is bounded away from 0, but we have a subsequence which actually its limit is 0. That's the contradiction. So this equals 0, which contradicts the fact that this is bounded away from 0. So not only is it not 0, but none of its subsequences or nothing go to 0. There you go. A whole lot of just kind of using this and that definition in particular order. I hope that you can kind of hold it all in your mind at once. It's a little complicated, although we are just using the definitions for most of the steps. All right. Any thoughts about that? This is all that I want to say about uniform continuity. All right. The slogan is, if it's continuous, pointwise, and you are on a compact set, then it's uniformly continuous. All right. Great. Let's talk then about the intermediate value theorem. That's the other thing I wanted to talk about today. This we may talk for more than just today about. I don't know. We'll see. The intermediate value theorem. So I will refresh our memory. I hope you all remember the intermediate value theorem. Intermediate value theorem. One of the three big value theorems, in my opinion. There's the extreme value theorem we talked about before, which is that a continuous function on a compact set has a minimum and a maximum value. The intermediate value theorem. There's also the mean value theorem, which is about slopes, really, which I don't want to talk about because we haven't talked about the derivative. But the intermediate value theorem, does anybody remember this one? Yeah?
Isn't it like if you had, it's like you have two numbers, it's definitely something between, right?
Yeah, it's about something between something. You remember?
If something's, if the function's continuous and there are two values on that function, then there's a value between them.
Yeah, something like that. Like the very simple version is if you have a continuous function and its value is positive somewhere and negative somewhere else, then it has to be 0 somewhere in between. Or you can say more generally, if it just has two separate values and any value in between must be achieved by the function at some point, because it can't jump from one value to the next if it's continuous. It has to actually go through all of the in-between values. So the typical way that this is stated, I will say it like this. I'm going to give you the version sort of from calculus in terms of closed intervals. But I want to talk, as we have for these other ones, I want to talk about, is this really about closed intervals? Or maybe it's actually about compact sets? Or maybe it's actually about something else? I don't know. Anyway, I'm going to say let f be continuous on a closed interval. Just point-wise, doesn't have to be uniformly continuous. And then if here's how it's written in our book. If f of a is less than L is less than f of b, that is to say, if there is some other number in between the two endpoints when you plug it into the function, if there's another in between, or here I've assumed that the left endpoint is lesser, but it could be the other way around. So or f of b less than L less than f of a. It doesn't matter. It has to be one way or the other. If there is some number that's in between the function values on the endpoints of your interval, then there exists C in the interval a to b with f of c equals L. If there is some other value in between the two answers, then actually that value is achieved by the function at some point in between. And the picture you should have in mind is something like, let's say here's A and B. If it's continuous, then that would be f of A. Let's say f of B is up here. Then no matter what other point you choose, say L in the middle there, this at some point has to actually cross through L, right? If it's continuous. Why is that true? I mean, I just said, like, informally, it's true kind of because if it's continuous, you know this function cannot jump across any intermediate values. It has to actually run through all of the values in between, which is why the intermediate value theorem is true. All right, that's not a proof. I'm just saying that's what your intuitive notion should be about. All right, I thought so. I want to talk about a more abstract version of this, where it's not necessarily about a closed interval, because that's what I wrote the theorem in terms of a closed interval. But actually, it's not really about closed intervals. It's also not about compact sets, though. But I thought actually before, we got 20 minutes. I don't know if I want to actually do the proof of this within the next 20 minutes. Can we do like a fun little application of the intermediate value theorem? This is not an application in the way that like ordinary people talk about applications. This is like application to another bit of abstract mathematics. But here's how about things you can prove using the intermediate value theorem? Using the intermediate value theorem. There's a famous theorem in topology called the Borsuk-Ulam theorem, and there's a great book called Using the Borsuk-Ulam theorem, which is all about ways you can prove other abstract theorems using the Borsuk-Ulam theorem. It's not about using it in your own real life. You will not use the Borsuk-Ulam theorem in your own real life. The intermediate value theorem. How about I would like to prove as a theorem. This is something, I don't know if you've ever actually tried to think about this. Square root of 2 exists. We can prove this using the intermediate value theorem. I don't know if any of you have ever wondered about, does the square root of 2 really exist? It does. I think kids think it does because your calculator has a square root button on it, and I push the button and something happens. So I guess that's the thing. When I do like the square root of 2, it's a real thing. But it's not obvious that the square root of 2 exists. I'm going to write this in a more sophisticated way, which makes it seem even less obvious, i.e., there is some number, I will call it x, a real number with x squared equals 2, right? When I write it that way, it's, I don't know, less obvious maybe. Is there really some number x which obeys x squared equal 2? Your instinct will be, obviously it's the square root of 2. But it's not so obvious to me. Like, for instance, there is no real number with x squared equals -1, right? You can say there is such a thing as that, but it's not a real number. It's an imaginary number. What's so great about 2 versus -1 that makes this one true and this one is not true? There's some kind of reason why we say this one is true, whereas this one is not true. There is you can do imaginary numbers, but you don't get a real number, right? I'm saying you get a real number here with x squared equals 2. This is something to discuss, I think. All right. Anyway, we can do this using the intermediate value theorem. Check it out. I'm going to turn this into a function. You have to talk about a function when you're talking about the intermediate value theorem. So I'm going to say let f of x equal, and the function I want to use is x squared minus 2. All right. And so our goal then is to show that there's some number which makes that equal 0, right? Because if this equals 0, then that means x squared equals 2, which means that the square root of 2 is a real number. So really what I want is, we want a real number, I'll call it C in R, which makes f of c equals 0, right? Then that will be the square root of 2. How can we demonstrate that such a real number actually exists? Well, you can use the the intermediate value theorem. I actually gave a clue. What I said before, I said there's a simpler version of the intermediate value theorem which says if you can plug some value in and get a positive number and some other value in and get a negative number, that means somewhere in between there has to be a value where the answer is 0. Actually, that's exactly what I want to look for here. I'm trying to find some number which makes f of c equal 0. So can anyone suggest? Is it possible to say, can you tell me some value where you plug it in and you get a positive, and then some other value where you plug it in and you get a negative? What do you think? You got one or the other? This is your function. This is not really hard to do. This function, can you just tell me a number where you plug it in? Yeah. 1. Okay, so if you plug in 1, you get a negative, right? So I'm going to say f of 1 equals -1, right? And what's your other value? 3, okay. F of 3 equals 3 squared minus 2, which is 7, all right? We're actually in this this scenario right here. All right, so I can say, considering f on the interval from 1 to 3, it is a fact that f of 1 is less than 0, is less than f of 3. And so, by the intermediate value theorem, would you mind if I say the IVT? There exists a c in the interval from 1 to 3 such that f of c equals 0. I'm using the statement of the intermediate value theorem that I wrote where instead of the big L, I'm just using 0. And that's it, really. I mean, this is what I wanted to show. So that means that f of c would be c squared minus 2 equals 0. So c squared equals 2, which is what we wanted, right? The intermediate value theorem tells you. And in fact, as sort of for free, we have deduced that actually the square root of 2 is between 1 and 3, right? Apparently it is. Just because she said so. She chose 1 and 3 here. The square root of 2 is between 1 and 3. You could have also chosen 1 and 2, because then you get 2 for this. So in fact, the square root of 2 is between 1 and 2. It is. Yeah?
Do we have to prove that it's closed and like continuous, or?
So the fact that this is a closed interval, I would say you don't have to prove that. The fact that f is continuous, that's worth thinking about, although f is a polynomial. So we already talked about a few times ago, we proved that all polynomials are continuous. So I feel fine about calling that continuous. Yeah, it's good to think about though. I suppose, yeah, when I start asking you to like prove that somewhat obvious facts are true, you should start to doubt everything. But it's true. Yeah, that's continuous. All right. I had one more. How about, can we do this just a little bit more generally here? More generally? Square root of k exists for any k greater than or equal to 0. All right? It doesn't when k is negative. By exists, I mean exists and is a real number. All right? If k is negative, this is not a real number. But if it is positive, greater or equal to 0, then it does have a square root. I'm going to try and do the same thing, all right? It amounts to, again, I'm going to consider this function. Let f of x equal x squared minus 2. Sorry, not 2. What do I want instead of 2? K, yeah. I want something which when you squared it equals k. So I'm going to say x squared minus k. And then I want to choose some value which makes this positive, some other value which makes this negative, right? Can we do it? Anybody have just an idea? Last time we used 1 and 3, although I imagine she chose 1 and 3 because somehow you knew vaguely what the answers were going to be. In this case, what do you think?
Can you do like 0 and k?
0. Okay, 0 is a good idea because 0 will always give me a negative, right? So I'm going to write that first. 0 squared minus k is negative k is negative, right? Okay, that's great. What about, she said 0 and k. If I use k, this is another good idea. It's good to choose something involving k, and I suppose k is simplest choice involving k. This would be k squared minus k. Is that positive? Also known as k times k minus 1, I suppose. Is that always positive? I think it's sometimes positive and sometimes negative. For instance, this will be negative if k is a half, because then this would be positive and this would be negative. Yeah?
K plus 1.
K plus 1. I think you'll have a similar issue. You would get k plus 1, the whole thing squared, minus k plus 1. You do some weird FOIL thing to simplify. This is sometimes positive, sometimes negative. And this is not something you can get around by making a cuter choice. Actually, this is. Yeah?
You say k plus 1 over k, so it's always greater than 1.
K plus 1 over k. That still, I think, is sometimes negative. If k is negative a half, and you add
It has to
1.
be greater than or equal to 0.
Okay, okay.
If it's just going to be really messy in the equation.
This is not how I was thinking of doing it. Hmm? K plus 1 squared. All right, I will try. So you're suggesting f of k plus 1? This is what she said before. I didn't like it before, but maybe I should have thought more carefully. I don't know. We'll see. Like that?
I think that works.
That's always positive?
Because it's supposed to k squared plus k plus 1. And that's all positive.
Yeah, I like this. This is not what I was going to do. So my instinct was to say I didn't like it, but yeah, I changed my mind. Thank you for your persistence. Yeah, this is always positive because k is positive. I like that. This is better than what I was going to say. Is positive since k is positive. All right. Excellent. And so let me just let's see if we can sort of conclude. So on the interval that I'm considering is 0 to k plus 1. F of 0, which is negative, is less than 0, and f of k plus 1 is positive. So from now, I'm just writing the same stuff that we wrote at the end of the first version of this proof. So there exists a c in the interval, 0 to k plus 1, with f of c equals 0, i.e. c squared minus k equals 0, which means c squared equals k. Excellent. I do have one last nitpick about this. If k is 0, as I said, this theorem is supposed to be true for any k greater or equal to 0. If k is 0, then actually this is not negative. This is just 0. And so we don't have this thing on both sides here. So can we make I think the most sensible way to get around this is just to make a special argument in the case where k equals 0. Can we just prove the thing directly in the case where k equals 0? So as a special case. I wrote case with a K, pun intended. Special case when k equals 0, all right? Is it possible to make this happen just with some kind of special arguments if k is 0? Remember what we're trying to demonstrate is, i.e., find c with c squared minus k equals 0. Can you find c with where this is satisfied in the case when k is 0? Yeah?
Well, there's definitely a lot of just thinking like, I don't know, it's kind of weird. It's that you end up with c squared equals
Yes.
k is 0.
Yeah, so can you tell me if k is 0, can I just say, i.e., this is the same as that, right? Is there, does anybody know some value of c for which c squared equals 0? The answer is 0. Yeah, really, if you think about it, what I'm asking you is there a special argument which we can use to demonstrate the square root of 0 exists? The argument is, yes, it exists. It equals 0. That's all you have to say, right? We couldn't say that in the other ones because you can't say the square root of 2 exists. It equals whatever. I mean, it equals some random irrational number. But for 0, you can say very specifically the square root of 0 exists and it equals 0. So c equals 0 satisfies this. So that's my special argument, right? Find c where c squared minus k equals 0. If k is 0, then c equals 0 is the answer. The square root of 0 is 0. That's what I'm saying. All right, that was a little technicality. in our remaining 4 minutes, maybe we could discuss. This is where what I want to talk about, remember, is the intermediate value theorem. But for sets, I want to talk about what exactly is it about the closed interval which makes this work. So the picture you should have in mind is like this. And the function does something like that if it's continuous. Maybe lots of little wiggles, but it does something like that. All right, it's continuous. Now, what is important about this is that any value you choose along here actually has a function value associated with it. So, I could pick the L right there, and this L is guaranteed to actually hit one of those the function somewhere. All right. This, my friends, is not actually about a compact set. A lot of times we've taken theorems which are about closed intervals and said actually those theorems are also true of any compact set. This is not actually true of any compact set. For instance, like this closed interval, right? That is a compact set, but I could change the closed interval to another compact set. Here's another picture using a different compact set. How about this interval together with that interval? That's a compact set. I mean, it's disconnected, it's in two pieces, but altogether it's still closed and bounded. So altogether, that's a compact set. But this set no longer has the intermediate value property, sort of for obvious reasons once you think about it. The function, even if it's a continuous function, it means it does something like that over there and then something else over here. And now, if I have the one endpoint and the other endpoint, is it still true that any value I choose in here is actually appears as one of the function values? It is no longer true, right? If it is possible in this case to choose some L which never hits the function at all. All right. It's not about compactness. That's what I'm saying here. Actually, it is about something else. Anyone remember another property of sets that we talked about around the same time? Yeah. Connectedness. Yeah. This is not compact. And it's not true. But really, the reason that the intermediate value theorem fails here is because it's disconnected. It has a big hole in the middle, right? That's the important property of when we wrote it here in terms of a closed interval. Actually, it doesn't have to be a closed interval. It's just any connected set. If you have any connected set here, then the values, here, check it out. What I'm saying is, if this set here has no gaps in it, then the values here also have no gaps in it. Actually, the theorem is about connected sets both ways. It's about if you have a connected set in the domain, then the answer is also connected, meaning there's no missing values in the answers. All right. So the true version of the intermediate value theorem, and this we will talk about the proof of this next time. This is the senior math major level version of the intermediate value theorem, which when I write it doesn't even look like the intermediate value theorem anymore. It just says if f is continuous and E is a connected set, then f of E is connected. This is the super ultra genius version of the intermediate value theorem. It basically says, it resembles the original intermediate value theorem if you think about it. The domain is connected means there's no gap in the domain, and that means there's no gap in the range, which is what the intermediate value theorem says. All right.